Professor James Gimzewski from UCLA, working in the California Nanosystems Institute. My talk today is about actually a new device we've developed which can actually emulate very complex kind of world we live in, whether it be biological systems that are complex, or whether it be, for instance, social behavior, things like Facebook, the types of complex interactions and emergent behavior that result from it. So we can actually generate emergent complexity in a nanoscale device for the first time.
I'd like to talk about some work we do. We do it principally in UCLA, in the Department of Chemistry and California Nanosystems Institute. And also part of the work is done in MANA, which is a next project, which has been running about 8 years. It'll run another 2, may run another 5, which is aimed at trying to build a brain, but not in the conventional sense of what you think of artificial intelligence and computation and so on. And previously I worked with Christoph, actually. We worked together at IBM, and we were doing very kind of reductionist things like moving carbon monoxide molecules around and looking at different types of molecule systems. So I tried to introduce this talk, which also involved DARPA, SRI, HRL, which is formerly Hughes Research Laboratory in Malibu. We were involved in this project called Physical Intelligence, but to give you some kind of background to the device I'll talk about, it was 1985, that's about 30 years ago. I joined IBM in '83. We did some experiments which first were inadvertent experiments where the tip would crash into a surface. This is a silver surface, and it would make a bump. So anyway, this is how topographies looked in 1985. We never had a computer. We actually used a chart recorder for this, and there was a clever way to use a chart recorder to make it like a topographic map, and then we touched the surface and we could see a bump. But from that came this paper, which was published 87 or so, in which we approached with a tip to the silver surface, and then we could see, when we look at the logarithm of the current, typical a tunnel barrier, you see this exponential rise in the current, and then at some point it tailed off as the tunnel barrier collapsed, and then we made a point contact. And the resistance of that point contact was about 2e squared over h, which at that time would be Charvin's resistance, or later von Klitzing likes to call it the von Klitzing constant, but it's a fundamental constant to do with an atomic electrical contact. And then about 10 years ago, Masa Iono, who is a good friend of mine, we work together now, he found that by actually using a silver structure which was sulfided, so it contained silver sulfide, you could migrate silver atoms from that structure and make a point contact or multiple point contacts. So here you can see, for instance, this is in these units, e squared over 2h, this is 1 contact, 2 contacts, 3 contacts, and then you could go back and reverse the process. And that was really the basis originally of a type of device which is actually compatible with CMOS. This is one of the types of crossbar devices they made, and their idea was to make a memory device, essentially, in which the thing goes on and off. And this was inspired actually by using a tip which is made of silver, which was sulfided, where he was able to deposit, this was earlier and it's from a patent, he was able to deposit silver atoms on the surface, because you drive the system from a stoichiometric state, thermodynamically stable state, into a non-stable state by the application of the voltage, which causes the silver sulfide to lose some silver atoms, and the silver atoms to be then deposited on the tip. And it was very interesting, that work. And then about 12 years ago, when Heine was still alive, and this is Mark Welland, where is he there, looking happy as usual. We were in a conference in Sardinia, and this guy was from Fiat. He wanted to have a device that could pick up some kind of brain waves when people fall asleep in the car, because that's a fairly common cause of people dying in cars. They fall asleep. And this guy works in robots. He's from San Diego. I've forgotten his name, Requia or so. And at the end of this think tank, there was about 25 people involved. We came up with this as a conclusion, which is challenge, understand, and communicate with the brain. So I wasn't thinking of the brain there, but I found this thing from many years ago, and it's strange sometimes you think of something many years ago and it comes to pass. So when I was working in Japan, the Japanese were trying to get the atomic switch, as it's known, to go on and off. That was their idea. You know, switch on, that's a memory state 1, switch off, it's a memory state 0, and maybe they could multi-state memories in this process. So just because I'm kind of the way I think, I was thinking, how would this thing operate if we operate it in a voltage somewhere between on and off? What would it do? And we discovered actually that it behaves somewhat similar in some manners to a synapse in the brain. And you know, there's various models, a psychological model for memory, Atkinson-Shiffrin model, in which you have some incoming information, sensory memory information. It goes into a short-term memory, and then you basically forget it. But by a process of rehearsal, if you rehearse it frequently enough, it will go into the long-state memory. That's a psychological model. And in terms of potentiation, short-term potentiation, long-term potentiation, it's a similar process. So this is what we did. We actually set up with a scanning tunneling microscope, we started to stimulate the surface of a sulfide-coated silver structure. And what we can see here is that we apply pulses. This is like 2 per 50 seconds, but here it's more frequent. If we do it infrequently, it will go into a state which is this E² quantum conductance state, and then it will return to the initial state. And as you repeat the stimulation, it does show some indication that it memorizes for a longer time, but not much. It will. So this is the equivalent in our scheme of a short-term memory. And if you do it frequently, then it will go into a more permanent state. And if you leave it long enough, it will then forget. So this would be memorization. This is not memorization of the stimulus, short-term and long-term memory. And so we stimulated a whole bunch of areas of the surface with stimuli here. So you see when you put this number 2 as a stimulation, the stored image starts to forget. It's short-term memory. And now when we do the number 1, which is much more frequent, you'll see how it goes into a more permanent memory state. So we had developed a system, it's also known as the multi-store model, which resembled a single synaptic connection. And it's inspired by biological systems. And basically, from there, we started to think about how we could firstly simulate this, and there's some mathematics here based on memristors, and basically we have the sulfide Ag2S medium, and then we can look at how we can make these nanofilaments, which are believed to be responsible for the memory. So thicker nanofilaments are longer-term memory, thin ones are short-term memory. And in fact, if you use that type of simulation, this is the experimental data, this is simulation, agrees quite well with the data that we measured. So schematically, the situation would look like this. As we pulse it, short-term memory, we can make this single atomic chain, for instance. And then as we repeat it, we start to build up a thicker nexus over atoms, which then cause the memory process. So that's in silver sulfide. It also works in copper sulfide, and also works in these tungsten suboxides. And in the case of tungsten suboxides, we can actually make more permanent memory, as well as a variety of devices. So for instance, we can make quite a more permanent structure here, which would act as a diode, as well as exhibiting long-term memory if we want, depending on the conditions. We can work it as a capacitor, we can work it as a resistor. So in theory, you could actually build up different types of electronic circuits with, including even a 3-terminal device. If you have two electrodes, input electrodes in close proximity, they will actually move the sulfur from one side to the other and cause a 3-terminal type device. So that was all fair and well, and DARPA had a big program called the Synapse program, which was aimed at creating synthetic synapses. We weren't involved in that program, but we became involved in the next program, which was called Physical Intelligence, which was the idea to make a physically intelligent system that could think in some ways. And our approach was to start to think about the brain, and if you look at the structure of the brain, it's a very sort of dendritic network-like structure, particularly in the neocortex, which is very highly dense in these unmyelinated synaptic connections. So we started thinking about the idea that we could generate a network of these synthetic synapses. And when you think of networks, there are various types of networks: small world networks, scale-free networks, random networks, hierarchical networks. Scale-free networks are particularly interesting. When you have a network here where you have many nodes in the network with few links, and the absence of like hubs with many links, you get this Poisson-like curve, okay? And in physics, that type of thing. In the real world, both in the biological world and the world we live in fact, things resemble more scale-free networks, in which you have a situation where you have certain points here that have many connections and other points that have few connections. And actually, the points with many connections have a higher probability to make connections than the points with fewer connections, proportional in some ways to the number of existing connections in the hub. And they exhibit this this is the number of links, and this is the number of nodes within the link. You see there are few here with many links or hubs, and many with few. And this type of network is very persuasive in our society. So as an example, what you see here is internet activity worldwide, and as the day goes past, you can see some changes in activity. But these can be described in terms of scale-free networks, in the sense that you have many hubs that have many connections, okay, and then ones that have fewer connections. In biology, there are many examples of this type of interaction. This is from yeast, and you'll find that certain proteins in the yeast will bind to many proteins, and other ones won't bind to many, and there's fewer of those that bind to many. So they're critical in terms of life. In terms of financial markets, it's similar. There are certain banks and so on in the financial system that are connected to many, and then other ones that are connected just to a few. So that can be thought of in that way. And then if you take social networks, like Facebook, you have a similar situation. You have, some people that have many friends, like I've got 4,700, and then you have people that don't have many friends, and then you tend to get more friend requests when you have many friends. And the whole world as we know it is actually a massive network like this, not only inside ourselves, but outside. And you have ISIS, you have the NSA that everybody knows about, that's snooping into our networks and trying to understand something about the social, system and terrorists and so on. Now, all networks are not necessarily following these scale-free networks. So if you take highways, they don't. You can have a situation where these networks can break down easily if you knock out a few nodes. But if you take airline systems and you just randomly knock out an airport, it won't have many effects. In terms of the distribution, these would follow this type of bell-shaped curve in terms of the number of links, the highways. Whereas you take airports, you have some airports like LAX that are hub points and connected to many, and they have this power law distribution, which is generally described by a linear log scale of the number of links versus the number of nodes in the hub. And very briefly, if you look at accidental node failures in the roads works, you can lead to a situation where it quickly deteriorates, whereas scale-free networks are very robust, and you can knock them out randomly and nothing happens, unless you have a deliberate attack on the hubs, and then you can bring down the system. You can knock out a lot of random nodes in the scale-free, and the system still works. So we wanted to make a machine that could simulate this type of behavior, and that's the aim of our research. It's not really a computer or AI in some ways. It's you could call it a complextor or something instead of a computer. It's interesting when you look at scale-free networks. Crystal lattices don't behave like that. If you take one atom out, everything is more or less much the same. But cellular metabolism, Hollywood actors, there's certain actors that got all the parts, the internet, and you go down here and sexual relationships. So if you look at, there are some people in the world, not me, that will have many sexual relationships with many partners. And there's a few of them, and they're these hubs, and then there are people that, they more or less have one or whatever, one or none or two, or something like that. Anyway. Now, when computers try to actually model this type of complex behavior, they really have a problem because of the complexity. How do you do this? And, for all the, deterministic tasks, where much money is in your bank account, they're fantastic. But when they try to look at stock markets, earthquakes, all these things, the system, or even bird flocking, or animal swarming, they really have a problem. However, that has not stopped people, so aside from the effort in Lausanne on trying to simulate or recreate the brain in a massive computer, you have IBM Watson, which is billed as a natural language AI computer, and it's got a lot of press, and IBM, we know, Christoph and I know, are very good at getting press. But how that thing can scale up is a problem, and I'll show you why. Or some evidence. And the K computer, which is a very powerful supercomputer in Japan, I think the most powerful one may be China at the moment, but practically every month somebody has a more powerful one. In order to, this one was able to simulate, it's a type of simulation on brain activity. It has 80,000 nodes, 10 petaflops, 16 billion operations per second. It uses the power of 10,000 homes, and it took 40 minutes to simulate 1 second of activity of 1% a human brain. And even then, it's, dubious. And the predecessor to Watson was able to apparently simulate something like a quarter of a cat's brain or something for a second or 2 seconds, and took a long time. So the reason for this is due to the fundamental architecture of computers. And in computers, as we know it, which is actually based on the concept of Alan Turing, the von Neumann kind of architecture has a bottleneck in that information has to go from memory to processor back and forward in this manner. And in addition to that, fundamental limit when you try to deal with complexity, you have the problem of heating these days, which is immense as you make things smaller. Quantum mechanics, tunneling processes, doping. What does doping mean when something's so small the doping atom might be there or might not be? And entropy, because every operation involving memory involves this energy kT log 2, which is the fundamental concept of Maxwell's demon in Feynman, you know, when he talked about the ratchet and Paul and perpetual motion. So the aim of the DARPA project, and it wasn't, we're not supposed to make something really, but was to try to see how could we go from this problem here. This is a logarithm, this is a logarithm, this is simple and complex problems, and this is machine complexity. How big the machine is, you know, how many, you know, transistors, memories, whatever. And in the case of von Neumann machines, you see the problem blows up. So if you try to approach the human brain, not even a nuclear reactor, all the power from a nuclear reactor, electrical power is not going to solve it. And you can fill up this whole place with computers, you're still not going to solve it with this fundamental von Neumann architecture. So we are looking at, it's called Neuromorphic, which was originally Carter Mead's idea, which was a kind of embodiment of some kind of synapses or neurons in silicon, but the word more is brain-like, maybe is a better word. But they have this capability, and I'll show you why, to actually, at some point, overtake the von Neumann machine. Not in accuracy or speed, but in terms of more human-like, brain-like tasks. And you know, even if you consider all the, you know, the cells in your body that are sending information constantly to you, have smell, taste, touch, hearing, vision, so many, you know, thousands of these cells. It's a really complex problem because a brain by itself is nothing, in my opinion, unless it has, you know, input from the outside. Alan Turing actually did, in addition to his concept of the Turing machine, which became, you know, a von Neumann type architecture, he was thinking about things that could think. He was interested in the brain, and he came up with the idea of an unorganized machine, which was essentially a kind of random network in which you had these gates. I think there were NAND gates or something like that. And according to him, I haven't been able to prove it, but according to him, this machine could actually perform as well as the traditional kind of von Neumann machine. So our idea was actually to generate something that resembles the brain, and we picked the neocortex. The neocortex seemed to be a good area. You know, this is the more highly developed area of the brain, and in order to do that, we looked at the structure, and this is from Kajal, some of his famous plates. He actually used silver and so on to make these images, dyed them or so. And basically, we see this as internet-connected fiber, this network, these fibers, and about 60% by volume. And so, together actually with Walter Freeman, who's very famous in understanding the brain, we came up with the idea of Neuropil, and to actually synthetically generate Neuropil. So the way we did this was to start with actually order structures. These are on a nanometer, 100 nanometer scale or something, and there are a bunch of posts. No, sorry, micron scale, but micron. And we take these copper posts and we treat it with silver nitrate, which causes for every copper atom here makes 2 silver atoms. And in a clever way, we can then generate these nanowire structures that traverse the surface. And then we basically take those and then we sulfurize them, and then we generate at each connection of these wires, we generate a synthetic synapse. And normally, this process of silver nitrate plus copper, for instance, follows laws. They're called diffusion limited aggregation that gives you fractal-like structures or dendritic-like structures. And we found as we change the dimension of the copper posts, we can move from this to more nanowire structures, and it was due to the fact that we can avoid some instabilities that occur on the larger scale. So we're able to make these very nice nanowire structures. Here you can see you can have very long ones and short ones, and using this process of bottom-up fabrication using silicon technology, and then top-down fabrication using like CMOS process with bottom-up, we can then generate these structures, and you can see here many short connections, there are many long connections. It looks ideal, and each one of these has a synthetic synapse. And then we mounted these on electrode arrays. We built these. There are also MEAs used in neuroscience to look at neurocultures. And then we covered them with this. And we can achieve, at the moment, about 10 to the 9, 1 billion synthetic synapses per square centimeter. And in addition to that, we can electrically connect to different parts, just like you would do with an EEG, for instance, when you're studying the brain. So this is what the chip looks like, and if you have a good eye, you'll see some electrodes where we can put information in and out, and we do that not using multiplexing, we use that using continuous inputs and reading on the whole input-output structure. So the first thing we do here is to activate the network, and we do that by applying a voltage sweep, which moves it from this regime, which in memristor behavior is known as soft switching, to a hard switching regime, for instance, activation step. And then, unlike a single synapse, if we actually look at the behavior here, we see these spatiotemporal dynamics, where the current goes up, down, we have avalanche-like behavior, like the sandpile model, if you've heard of that, in terms of back, which is typical of self-organized criticality. And if we do it in this pulse mode, we can also see the observation of these metastable states. So basically, as we run this device, it starts to become activated both spatially and temporally. And in addition to that, it does actually remember the past, because all of these synthetic synapses have the short-term and long-term memory. In terms of the fluctuations, they exhibit these recurrent dynamics. And this shows, again, this log-log plot here. This is power spectral distribution versus frequency. It's not like 1 over F noise type thing we're talking about. This is this would be for an isolated switch versus when we have it in the network. And what you can see here is it's completely different. You don't get that log-log relationship. So here you see actually some of these different temporal stability, and again, power law relationships. We can do it in terms of the duration of the state. We can plot it several ways to convince ourselves that we have a self-organized system. So this is very similar, actually, I'll show you later, to how the brain is functioning. And if we look at these different electrodes, and this is correlation map, what you can see is there are some regions highly correlated and other regions that are not correlated. And spatially, there are motions where correlated regions become uncorrelated or even anti-correlated, which is also indicating the built-in dynamics of this complex system. If you actually look with a very high quality infrared camera at the heating in the system, you see that throughout this network, which is here, some peripheral stuff here, there is distribution of the electrical current. It's not like a single pathway through the system. And one of the other interesting features of the device is that it exhibits these higher harmonics in terms of when we look at the power spectrum, so Fourier transform. So you start to see these higher harmonics are amplified in the system. Okay, so we recently, I'll show you some other stuff. Recently, we also have been able to actually operate this device in a more constant current mode where we vary the voltage and map that voltage. This is the device. And if you just take a series of resistors, for instance, you can work out, if you put voltage in from one end to the other end, how these should behave. You know, you will have a situation where if you replace and move one resistor, you get a certain type of behavior, which is fairly predictable. If you look at the device, below an activation voltage, you'll get Gaussian noise. And here we have an example of the device. We have activity across the network, and you can see how regions, there are certain regions interpolated from these voltage signals that exhibit activity and how that activity moves through the network. So we have both this temporal dynamics and we have the spatial dynamics, which is really what we wanted. So let's look at the brain, and this is from Dante Gialvo, who works on fMRI. And if you look at brain activity, although it's partially compartmentalized, but in the process of thinking, you do get this type of also critical kind of dynamics. And if you take this data and plot it in different ways, you get power law behavior. This work is from Dietmar Plans at the NIH. If you look at neuronal cultures and if you look at the electrical activity by electrodes like we do, you also see similar power law relationships. And you know, the power law relationships may also relate to brain activity. So if we take these power law relationships, this is burst size, for instance, number of spikes versus number of spikes, and you take epileptics, you'll find the slope differs in those patients when they have an epileptic fit. If you take people that are sleeping versus people that are awake, you see the slope can change from -2 to -2.9. And it's just recently that we have been able to actually control the global dynamics of our device in terms of the lifetime of these states. And this indicates to us that it may be a very good system for a type of reservoir computation initially, which is called reservoir computation or echo state computation. This is an example here, more recent, how we can really change the slope of the activity. And we find that if we look at the current flowing through the system, this is the slope, this is the PSD slope, and this is another type of slope to do with the metastable states. You can see that we can actually modify at will the activity of the network. So in general, we can make the system in a very supercritical state, or we can have it in a critical state or subcritical state. And the supercritical state is very interesting in terms of models for the brain, as I'll mention in a second, and as well as reservoir computing. So one of the things we have been doing is a very simple thing that you do with rats. You take a rat and let it go down to this T, and you want it to go right or left, so you give it some kind of signal here, some kind of reward or something. And you see how far it can remember to turn right or left. And then you train it, and it's a test that's used. And we've been able to actually do that. This is our circuit where we have basically two inputs here. This is turn right, turn left. We have current flowing through it. Then we give them both a Q signal, and then we say let's say turn left, I guess, if you're going this way, that's the Q. And then we give them both a pulse, an action, and then we look for the reaction. And the reaction would be an indication if it has learned to turn right or left. And this is the result. It's rather hard to look at, but basically we're still working on the time delay, but we can achieve 94% correct. So without any programming, it can be taught to turn left or right depending on the signal it gets. It's also possible to memorize things in this device in unconventional ways. So if we put information in, the information is actually distributed. It's not located in a specific area of the system, just like the brain, although the brain has subcompartments. This is just an example of this type of behavior, which is a 2-bit memory device. And even though the inputs in terms of the network are spatially overlapping, we can separately store information in the system and read it out. So reservoir computation is something we do a little bit at the moment to keep was to keep the SNI people happy, but basically the idea is if you take these very noisy things, images that are rotated and so on, you have classifiers, output classifiers in regular computation, and it's a difficult task, speech recognition or so. So if we could take the data that comes in here and we can move it into higher dimensional space, that would be what we call reservoir computation in a way. And rather than use like a traditional, artificial neural network where we have to adjust all these nodes, this system we have represents a dynamic system. And of course this higher harmonic generation helps us. But basically the input signal here could be a sinus wave, for instance, and then we can look at these output signals, which are now spatially from temporal into spatial dimensions, and then we can see if we can obtain from this another type of signal would be, for instance, square wave, triangular waves, and so on. That ability to produce, for instance, output signals that would be square wave are favored by situations where we, for instance, have the activity in a higher activity mode so that we generate more higher harmonics. As I come to the end, I'll just make some little comments. Together with Walter Freeman, he's in Berkeley. Unfortunately, Walter was working on the brain all his life, and he recently had a stroke, which is kind of weird. But he's recovering. He worked on rabbit brains most of his life. And Robert Kozma, who works on neuropercolation theory, we've been trying to relate on, this is a more long-term project, but the Neuropil with the our chip, the atomic switch network, and he works on percolation lattice models for cellular automata models. And one of the interesting things about how this might work is that if you go from a subcritical state to a supercritical state, and there's so many theories out there, but Walter's theory is that basically as we're sitting here, we have these theta waves and alpha waves and brain waves. Basically you're going from a state which you could think is somewhat static in terms of the memory, the landscape of your memory, and then you're actually going mad for a second. I mean, you're going mad, and then you're saying mad, saying mad, saying. Everybody in this room is going like this. And based on the incoming information, that relates to how, in this mad state, it kind of drops down into a landscape. You could imagine it as the landscape, like of the desert, for instance, okay? And so these sand piles are building up, which are actually collectively the memorization of something. So, like you see, you may see like a cup of coffee or something, and smell the coffee, and the cup has a shape, and you put all those pieces of information to remember when you were sitting in a bar in Rome. That's, it's not a computation process as we know it. And so the types of things we think we can do is predict the future. We think we should be able to predict the future in complex systems eventually. And already using these recurrent neural networks, actually people have tried to predict the stock market, but using software. Like for instance, how do Google stocks go up and down? And predicting the future is what physics is all about. So in the Newtonian world, we can always predict the future. The ball goes here, we know the equations, so we know where the ball will be sometime later. In quantum mechanics, we don't know. When we do one experiment with one electron or something, we don't know exactly what the outcome is because there are so many quantum probabilities, but if we do it many times, we do know. The world we live in the complex systems is maybe more related to the quantum world. And so there are all these temporal spatial trajectories that we would have to track. I think this actually is one before the end, which is, if we look at networks, and here we have the internet, I showed you earlier. Here we have the universe. Here we have the human brain, and here we have our device. And if you look at the time scales, this is trillions of years. In terms of the internet of things moving around, it's probably more like in seconds, network dynamics, For instance, some people monitored text messages. Orange in France monitored text messages when Madonna arrived someplace. And it took about 15, 20 seconds, if you look at the network, how the activity of the texting, what the word Madonna propagated through the system. It took about that. The human brain is probably 1 to 10 hertz. Our device at the moment can work at frequency in terms of these spatial temporal dynamics of the order of 50 kilohertz. And basically, one of the interesting things about the network, apart from having the short-term, long-term memorization, distribution of the memory, one of the interesting things about this particular network is you can view when it goes into a critical state, you can view that to be in physics what would be a second-order phase transition. So essentially, the correlation length goes, to infinity. So the information is distributed throughout the whole system. And that is a key part to the device's operation. So it's one approach, and we continue to do it. And personally, I also work in biology, which has inspired me actually to become less a reductionist in the conventional sense, and I love it. So I'd like to thank some of the people. These are people in my group, and actually Christina, she's returned to Switzerland now. And of course the MANA group, and then these are the people from HRL, SRI, and then Cosma and Freeman at Berkeley, and also the University of Memphis, which is doing theoretical work. And these are some of the people involved peripherally around the project, which were on the physical intelligence program, whose program manager or leader was Todd Hill. Thank you.